this. And in that, what we have done so far is that after the definition of an inner product space, we proved important properties of the inner product. And in that process, two important properties we proved. One was triangle inequality, but that was derived using the more important property, which is known as the Schwarz inequality. So what the Schwarz inequality said that in an inner product space for any two vectors u and v, the modulus of the complex number, the inner product u with v, is less or equal to the product of the norms of norm u times norm v. And after that, we defined when do we say two vectors in an inner product space are orthogonal or perpendicular or normal to each other if their inner product is 0. Now, in that context, we have seen that if we have an orthogonal set of vectors, that means there is a set of vectors which are mutually, that means any two distinct vectors are orthogonal. We proved that such a set is linearly independent. That means orthogonal vectors are linearly independent. And from here, we also obtained one important observation as a corollary that if W is a linear combination of a sequence of orthogonal vectors, then you can write this W as a specific linear combination where the coefficients come from the inner product. So W, a linear combination, suppose this is alpha k vk, where vk's are orthogonal. Then these alpha k's can be obtained as for every k1 to n as the inner product of W and vk divided by the square of the norm of vk. So this is what we proved. Now our ultimate goal was, if you remember, to prove that if V is an inner product space over F, where F is R on C and W is a subspace of V, and W perpendicular or orthogonal denotes the set of all vectors in V which are orthogonal to every vector in W. Then in case V is finite dimensional, actually the result holds in general that V is the direct sum of the subspace W with its orthogonal complement. The reason it is called orthogonal complement is because of this being direct sum. So if we want to prove that W direct sum W orthogonal is actually V, what we must show is that V is the sum and the intersection of W with orthogonal W is 0. The second property is easy to see and that we had already done. So what is remaining is to show that V is sum of W with its orthogonal complement. Now in that process, we shall be using what I described as a corollary that if W is a linear combination of a sequence of orthogonal vectors, then it can be written as a linear combination where the coefficients can be written in terms of the inner product. Now from here we can derive something more. So this theorem we can prove that let us say V be an inner product space. So let us say V be an inner product space. So inner product space. And let us take, see, if the vectors are orthogonal, then they are linearly independent, that we have proved already. Now what we want to see is the converse. So if we have linearly independent vectors, are they orthogonal? In general, obviously, this is not true. You can find simple examples. So for example, you take the vector say 1 0 and you take another as say 1 1, for example. Now these two are not orthogonal. You can see that if you plot the graph, then one is 1 0 is parallel to x-axis, and 1 1 is the graph which is parallel to the line y is equal to x. And obviously, the angle between them is 45 degrees or pi by 4, and they are not mutually orthogonal. So linearly independent vectors are not orthogonal. And in that case, the question is that can we obtain from a given set of linearly independent vectors orthogonal vectors? So this theorem says precisely that, and this process of obtaining these orthogonal vectors is called Gram-Schmidt orthogonalization. So we are doing what is called Gram-Schmidt orthogonalization. So let V over F be an inner product space, and let us take we have vectors say V1, V2, and say Vn in V be any linearly independent vectors. Independent vectors. Then we can obtain orthogonal vectors, say W1, W2, say Wn in V, orthogonal vectors. So they are mutually orthogonal. That means that Wi with the Wj inner product is 0. So orthogonal to each other. Can be obtained from V1, V2, Vn, such that in case V1, V2, Vn is a basis, so then W1, W2, Wn is a basis. So such that this is set W1, W2, and Wn is a basis for the subspace W, which is spanned by is the linear span of say V1, V2. This process of obtaining orthogonal vectors W1, W2, Wn from V1, V2, Vn. Now this n is not as such required to be finite. For any n that can be. And this process is called the process of obtaining orthogonal vectors from linearly independent vectors is called Gram-Schmidt orthogonalization. Process. So let us see how this can be done. So as proof how this can be done is so we begin with the say first vector. Since V1, V2, Vn are linearly independent, so each of them is non-zero. You can start with anyone. So you can start with say V1. V1 is not zero, and W1 you take V1. V1 is linearly independent, so this is not zero. So start with W1. and take this W1 to be V1 itself. And now to obtain the next, suppose we can obtain for some K, and then we shall prove that for K plus 1 also can be obtained. That means what we are doing is we are using the process of induction on N. So it holds that for N equal to 1, this can be done by taking this. So now suppose we are successful in obtaining W1, W2, Wk obtained. For say K is some N. So for say K is equal to M, up to that we can obtain as an orthogonal basis. As an orthogonal basis means it is a basis and the vectors are usually orthogonal. For the subspace spanned by, that means it is V1, V2, V. All right. So the question is the next vector Wk plus 1. And up to M it is, so what is the Wm plus 1? So for this, now let us take this W m plus 1 to be the vector Vm plus 1 minus this K is equal to 1 to M, and this is here. So Vm plus 1, Vm plus 1, inner product with Wk divided by the norm of Wk squared. W. Now this is the vector, let us take. So Vm plus 1 minus this linear combination of W K's K1 to M. Now this is a vector in V obviously. Now take the inner product of this with Wj. So Wm plus 1 J. So this is the inner product when you take with the Wj, we should be using that inner product is linear in the first coordinate, and therefore the inner product of Wm plus 1 with Wj is Vm plus 1 inner product with Wj minus this sum. So this linear combination, so this will come out. So this is K is equal to 1 to M. This is a scalar, this inner product Vm plus 1 Wk divided by norm of K. This comes out. This is Vm plus 1 Wk divided by norm of Wk square, and then here you have Wk, Wj. And this holds true for all J. This holds true for all J 1 to N, and take for any. So 1 to N, because they have taken. Now Wj is, so this varies up to M, because Wj's we have up to 1. Now, since W's are orthogonal mutually, so when K is J and K are different, then it is 0. Otherwise, this is 1. This it is sum taken over K. So when K is equal to J, this becomes 1, and only one term will contribute from here. So first is as such Vm plus 1 Wj minus, from here what we have is when k is equal to j. So this will be Vm plus 1 Wj by norm of Wj square, and this will Wj. Now this inner product Wj with Wj is actually, you know that this is simply norm of Wj square, and this is in the denominator also, so this will be 1. So this will be simply Vm plus 1 Wj minus Vm plus 1 Wj. Now this is simply 0, and this holds true for every j. So our choice for Wm plus 1 as Vm plus 1 minus this linear combination works, that this is orthogonal to every vector W1, W2, Wm. So W1 plus 1 is the new vector that we can obtain now from the given set of linearly independent vectors Vm, V1, V2, Vm plus 1. And being orthogonal, they are linearly independent, and since the subspace spanned by V1, V2, Vm plus 1 is finite dimensional, and in that case, this becomes a basis. So what we have here is, so what we have got is that this is at W1, W2, and M plus 1 is an orthogonal set of M plus 1 vectors in V. Since they are orthogonal, therefore they are linearly independent also. As and therefore that this set W1, W2, Wm plus 1 is an orthogonal basis for the linear span of V1, V2, Vm plus 1. Since this is subspace and this is finite dimension, because this is spanned by a finite number of elements, and therefore they will be spanning. So this becomes an orthogonal basis for the subspace spanned by V1, V2, Vm plus 1. So the process holds for the vectors V1, V2, Vm plus 1 also. So starting from V1, V2, Vm, assuming that, we can also see that this process gives me the next set of orthogonal vectors. And therefore, hence this way and this way proves by induction that W1, W2, Wn can be obtained as an orthogonal basis for the linear span, so W, the linear span of V1, V2, V3. So what we had seen here is that for a basis, if we have V1, V2, Vn for a finite dimensional space F, we can obtain an orthogonal basis. Now, particular cases, if we want to see, we can also get it. So, in particular, we can see that W1 is V1. And you remember that this Wm plus 1 is Vm plus 1 minus the linear combination k is equal to 1 to m. This is Vm plus 1 Wk divided by norm of Wk square. And then you have, this is the coefficient, so Wk. This is for every m greater or equal to 1. So this gives me that if you want to know what is W2, so W2 is V2 minus. So sum is up to m is 1 in this case. So this will give only one term, and that will be this V2, and this is W1 by norm of W1 square W1. So this is for m is equal to 1. So m is equal to. So likewise, when m is equal to 2, so what do we get? M is equal to 3. So this will give me W3. So W3 is V3 minus. So there will be 2 here terms coming out from this sum. And what are these 2 terms? So the 2 terms from here is V3 and this is W1 by norm W1 square 1 minus V3 W2, because W1 W2 we have already determined, then this is norm of W2 square W2, and let us say m is equal to 3 will give me W4. So V4 minus V4 W1 norm W1 square W1 minus V4 W2 norm W2 square W2, and one more term that will be V4 W3 by norm of W3 square W3, and so on like that. So the Gram-Schmidt orthogonalization gives us this. Now I think we must prove what we wanted to prove, that W and W orthogonal basically sum into V. So orthogonal complement means W orthogonal. So we can prove now this theorem. So what this theorem says is so if V is a finite dimensional unit product space, finite dimensional product space, and W is a subspace of V, then V can be written as the direct sum of W with W orthogonal. Remember where what is W orthogonal. This is this set of all vectors in V which are orthogonal to W for every W in W. Yes. So this is what we want. We had already proved that the intersection of so we have already proved that W orthogonal is a subspace of V and intersection of W and W orthogonal is 0. So what we need to prove is that we need to prove that V is their sum. That's all. Now since V is an inner product space, since V is an inner product space and W is a subspace, we get W also to be an inner product. Now once inner product space and dimension of W over F, which cannot exceed the dimension of V over F, and this is finite means this is also finite. So this is a finite dimensional inner product space, the W. Once it is a finite dimensional inner product space, it has a basis, it has a orthogonal basis, and if it is having orthogonal basis, it has orthonormal basis, because what you do is you simply divide by norm of that. So W has orthogonal basis. So W has an orthogonal basis, say W1, W2, and WR for W over F. Without any loss of generality, we can assume that this is an orthonormal basis. Why? Because simply we can divide by norm of Wi for each I, and that will give that the norm of this new set will be 1. So we can assume that this is an orthonormal basis. So in that case, here, so if say V is a vector in V, then the vector U you can take, which is V minus the linear combination of V comma Wi, I is equal to 1 to R. Remember, when it was orthogonal, then this coefficient inner product V comma Wi was divided by norm of Wi square. And if you are assuming that this is orthonormal, so you can simply put for normal Wi square as simply 1, because normal Wi, if it is 1. So square is also 1. So now you can see this is say same as V minus W, where W is this. I is equal to 1 to R, V comma WI, WI. And that will make that U, the vector U, which is V minus W. So this will give that W is basically, you change the sides, then this is U minus V. So this will make that W is U minus V minus, sorry. V minus. Now W comma Wj therefore would be what? So V comma Wj minus U comma Wj. Okay, now W comma Wj. So W is our I is equal to 1 to R, and this is your V comma Wi, and therefore you can take this W comma Wj. So W comma Wj inner product. So because of this linearity in the first coordinate, V comma Wi comes out, and what we have here is Wi comma Wj. The sum is over I. When I is different from j, this is 0. Only one term will come from here. That will be when I becomes j. E Wj, and this is Wj, j. E comma Wj. Since Wj, this is norm of Wj square, and if you say that this is a set of orthonormal vectors, in that case this is 1. So W comma Wj is simply V comma Wj. Now we can see that U comma Wj, and recall U is V minus W. So U comma Wj, so U comma Wj, this is simply V comma Wj minus W comma Wj. And W comma Wj is V comma Wj. So V comma Wj minus V comma Wj. And this is simply 0. So what we see is that U comma Wj is 0. That means this U, this is in the so hence this means that U is orthogonal to W. J, and this is true for all J, 1, 2, R. So this means that this is 0 for every I, 1, 2, R. So that means this cannot be, U cannot belong to the linear span of W1, W2, R. That means W. What does it mean? U cannot belong to W. Okay, so U cannot belong to W, and the W is spanned by, say, this W1, W2, WR. So where does it? So that makes sure that this U is orthogonal to every vector because in W, because this is orthogonal to every basis vector. So what we get is that U is orthogonal to the whole, or U belongs to. So what we have got, U belongs to orthogonal. So V is now, here you can see, is U plus W. This V is U plus W, and U belongs to orthogonal W, or better you write W plus U. So this is here in W, and this is in the orthogonal W. Now this holds true for every V in V. That means what? V is contained here in W plus W orthogonal. So V is contained in W plus W orthogonal. Now this is a sum. This is always contained in V. So what we have got is V is the direct sum. Because this was the only thing that was remaining. First, this is sum. First, this is sum, but this is this. And since we had already proved the W and W orthogonal, they intersect in 0, we get V is the direct sum. Next. So what we have proved is that for a finite dimensional vector space V, if it is an inner product space and W is a subspace, then this is direct sum of W with this orthogonal complement W norm. The result as such holds true for any arbitrary vector space, but we have done it for finite dimensional. One more interesting thing is that if you have an inner product space, no. So let us take VB an inner product space and WB a subspace of V. Then W orthogonal is also a subspace of V. And by this, therefore, W orthogonals, orthogonal, which we prefer to denote this like this, is also a subspace of V. So you can keep on putting orthogonal complements and you can get new and new subspaces. Really? No. Because this gives you back W. So you get W orthogonal complement, and if you do it once again, you get this. Further, W and W are same. Now these are same means as subspace. So for this, what you can see here is that W is contained in W orthogonal orthogonal. Since W in W means what? W comma U is 0 for every U in L. For the U is in L, then this is orthogonal to every vector in W. This is what it means. But that also means that W belongs to W. So what we have got, that W is contained here. For the converse, we can use this finite dimensional. Then dimension here. So for the converse, observe that for the converse dimension of V over F is same as the dimension of W over F plus the dimension of W perpendicular over F. And dimension of W and dimension of W orthogonal will be okay. This is one thing. Also, this is same as the dimension of W orthogonal plus dimension of W orthogonal. Since what you can see is that V is your W plus, so add some W plus W orthogonal. If you take the orthogonal complements, then also it is same. So this W orthogonal plus W orthogonal complement, and that makes, if you see here, this gives that dimension of cancel dimension of orthogonal on sides. This will give you the dimension of F and dimension of W are same. Since there are two finite dimensional vector space of the same dimensions, one contained in another, and that forces that the two must be same. One or two simple examples quickly we can take, and I think I'll have to see this. Quickly see some examples. So examples. So let us take V to be R2 over R and the standard inner product space. Inner product. The standard inner product for that means what? That if X is say X1, X2, Y is say Y1, Y2, V. That means this inner product of X with Y is X1, Y1, X2. And let us take W to be the subspace spanned by the vector, say 1. That means every vector is of the form this, and this is same as alpha for every alpha in R. Suppose this is the subspace of Now let us take say the U1 and take U1 to be say 1 1 and U let us take 1 2. Then U1 U2 are linearly independent. It's easy to see for R. And so you can take B2 as U1 U2 is a basis for V over F. F is R, V is art. Now from here you can see that U2 is not in W. W is spanned by 1 1. And U1, U2 are also not U1, U2. They are not. That is U1, U2 are linearly independent but not orthogonal. So we want to see the Gram-Schmidt orthogonalization. To get on B2 if U1 you get orthogonal basis for as follows. So suppose that is W1, W2. So this is the D3, the basis W1, W2. So W1 is we take U1, W2 is U2 minus U2 W1, norm of W1 is square and W1, which is same as U2 minus U2, W1 is U1, norm of square 1. Now U1 is 1 1 and that makes a norm of U1 is square root 2 and U2 was 1 2. So this is same as W2 as, so this is 1 2 minus. So the norm of U1 square is 2 and U2 comma W1 is you can check that this is 3 by 2. So this is 3 by 2 and U1 is 1 1. That you can see easily. The inner product of U2 with U1 is 3. So U2, U1 inner product is, here you can see 1 into 1 plus 2 into 1. 1 into 1 plus 2 into 1, which is 3. And the norm of U1 square is 1 U1. This 1 into 1 plus 1 into. So this is what is the vector, and now you can see that this is 1 minus 3 by 2. So this, you are minus a half, and here 2 minus 3 by 2. So this is half. And the B3 is W1, W2 This is your simply 1, 1 and minus half is an orthogonal basis of V over F. That can be verified that these two are linearly independent and their inner product is 0. So we shall stop here and we shall take up more examples on Wednesday, that is tomorrow. If you want from here, by the way, an orthonormal basis, also you can note that you can divide by the norm of this. That will give you orthonormal basis. 4. So that means W1 by norm of W1 comma W2 by norm of 2 as the orthonormal basis. So this you can see that this is half and half norm of W1 is half and the other vector here is minus 2 is an orthonormal basis. Okay, so we shall go. So thank you very much for your kind attention.
Thank you, sir.